Welcome to an introduction to the cross product. I want to start by talking about a few things that you should know about the cross product. First of all, the cross product is one of a few methods for multiplying vectors. So you may have already studied the dot product. That is one technique for multiplying vectors. The cross product is another, and there are others. And the cross product is also known as the vector product because it's the result of that multiplication process is a vector. This is in contrast to the dot product, which typically produces a numerical or scalar value. So the result of a cross product is another vector. The cross product only is defined for vectors in space, three-dimensional space, or R3. And the cross product can be found algebraically and is based on determinants of matrices. And while the cross product can be determined in essence algebraically, it also has a physical representation known as the right-hand rule. So in this image here, we can see, in essence, a vector A in the color blue, a vector B in the color red, and the colors really don't matter so much. The first vector in the cross product, if I align my pointer finger in the direction of that vector, and the second vector in the cross product, if I align my middle finger in the direction of that vector, then my thumb, if I extend it upward, will be pointing in the direction of the cross product of those two vectors. Again, this is a right-hand rule, and it can give you an indication of the general direction of the result of performing a cross product of two vectors. And so what's interesting here is that resultant vector, we'll call that vector A cross vector B. That vector is orthogonal or perpendicular to both of the original vectors. So let's dig in and take a look at finding the cross product in a more algebraic, algorithmic manner. So we set up the cross product as a 3x3 determinant, and we're going to use the vectors u, which is 2, -1, 4, and vector v, which is 3, 2, 5, to illustrate this process. So when I'm setting up the cross product, I'm going to do vector u cross vector v. Order here does matter. And in this 3x3 determinant, in the first row, we put the unit vectors I, j, and k. Notice these are boldface. This indicates that they are vectors, not variables. And so when we work with a cross product and we work with the unit vectors I, j, and k, we need to be sure that we indicate that those are indeed vector quantities and not variable quantities. So what we do is we expand this 3x3 determinant in the following manner. We move across the first row and we expand about each of the unit vectors in turn. Now in the second row, we put the first vector. We put vector u in the first, that's the second row. So 2, -1, 4 is vector u. It goes in the second row. And in the third row, we put vector v. So that would be vector 3, 2, 5. Now, as we expand, we're going to start with vector I. And so we're going to take vector I and multiply it, in essence, against the subdeterminant, the 2x2 determinant that is the result of removing both the row and the column of I. So if I remove both the row and the column of I, like so, I'm left with the submatrix -1, 4, 2, 5. So I'm going to take the unit vector I and multiply it by the determinant of that smaller matrix. Moving across that top row, I come to the unit vector j. Now, as part of the process, with this middle vector, instead of having addition across, we are going to subtract. So this is important when we're doing a cross product. We are going to subtract, then unit vector j, and like we did before, we're going to remove both the row and the column that j resides in, and multiply unit vector j by the determinant of that remaining submatrix, 2, 4, 3, 5. And then the same is true for vector k. So we're going to add, and we're expanding around vector k. So we're removing the row and column. And so the subdeterminant we have is 2, -1, 3, and 2. And so at this point, what remains to be done is to find the determinant of each of these individual smaller submatrices. And so what I can do is, when I do this determinant here, I'm going to multiply -1 times 5, then I'm going to subtract, I'm going to multiply 2 times 4. And so what that's going to give me is vector I times, I'm going to have -5 minus 8. So that's going to give me a -13 times I, unit vector I. I'm going to suggest that you pause the video now and do a similar process for unit vectors j and k, and then come back, hit play, and check the result. I hope you paused the video and worked on finding those determinants of the two submatrices for unit vector j and unit vector k. In either case, you can see how those were expanded out. You can see -2 times 5 minus 3 times 4 for j, and 2 times 2 minus -1 times 3 for k. So the cross product resulted in a vector that is -13i plus 2j plus 5k. And let's just remind ourselves that this vector is vector u cross vector v. Now, we did claim a little while ago that the result of a cross product is a vector that is orthogonal to both of the original vectors. Well, we just found vector u cross vector v, which was -13 to 7. And so the claim is that that vector is orthogonal to both of the original vectors. So I want to remind you of a property. It's down here in the lower left corner. Two vectors A and B are orthogonal if and only if their dot product is equal to 0. And that's a number 0, not a vector 0. Because dot products produce scalar quantities, not vector quantities. So if I want to show that this new vector, -13, 2, 7, is orthogonal to both the original vectors, all I have to do is show that the dot product of u cross v with u is 0, and the cross product of u dot v dot product with v is 0. And that will show that our new vector is in fact orthogonal to both of the original vectors. So let's go ahead and take a look at that. And we'll remind ourselves that u is the vector 2, negative 1, 4, and v is the vector 3, 2, 5. So let's go ahead and do vector u cross v dot product with vector u. So that's negative 13, 2, 7 dot product with u, which is 2, negative 1, 4. And when I do that dot product, I've got negative 13 times 2. I'm writing this out just for illustration purposes. 2 times a negative 1, and plus a 7 times a 4. That gives us negative 26 minus 2 plus 28. Negative 28 plus 28 is in fact 0. We can do the same thing for vector u cross v. So negative 13, negative 13, 2, 7 dot product with vector v, which is 3, 2, 5. And doing that dot product, we'll get negative 13 times 3 plus 2 times 2 plus 7 times 5. Again, illustrating that dot product, we end up with negative 39 plus 4 plus 35. That's negative 39 plus positive 39. So in fact, that is 0 as well. So this implies that vector u cross v is orthogonal to u, and that vector u cross v is also orthogonal to vector v. Let's go ahead and take one more look at a basic idea related to this cross product. So we should recognize these two vectors here as our original vectors u and v. And what happens is sometimes we want to have a unit vector that is orthogonal to two original vectors. So in this case, let's go ahead and find unit vectors that are orthogonal to our original vector. So first of all, we know that u cross v, which was equal to negative 13, 2, 7, is orthogonal to vector u and to vector v. So we already have a vector that is orthogonal to the two given vectors. So really all we need to do is think about finding a unit vector, and how could we get a second unit vector from the one unit vector. So down in the lower left corner, a reminder that a unit vector u with the same direction as some other vector a is found by taking that vector and dividing by its magnitude. So what I want to do here is I want to find the magnitude of this orthogonal vector. So I'm going to go ahead and find its magnitude. This is negative 13 squared plus 2 squared plus 7 squared, all under a square root. This results in the square root of 169 plus 4 plus 7. 7 squared, 49. And if I sum that, I get the square root of 222. Now it turns out that 222 does not have any factors that are perfect squares, so I'm going to leave that alone. So the unit vector that I want is, and I'm going to, I don't know, we've already used the symbol U, so I'm going to call it W, is going to be that orthogonal vector, so U cross V, that's the orthogonal vector, divided by its magnitude, so vector U cross V magnitude, and that's going to look like U cross V was negative 13, 2, 7, and then the magnitude of that vector was 222. So I can also write it this way, where each component of that orthogonal vector is divided by its magnitude. So great, we have one vector that's orthogonal and a unit vector. What we need to do is find a second vector. Now it turns out that that's not too difficult to do. If we multiply our original vector W here by -1, the vector will have in essence the same direction, just pointing opposite to the original. So think about it as possibly going forward along a line and then multiplying by -1, you're just moving backwards along the line. The line would have the same basic direction. So let's go ahead and do that. So if we take our vector W and we basically multiply it by a -1, that's just going to change the sign of each of the components of our original vector. And so what we end up with is negative W, our second vector, is 13 over the square root of 222, comma, -2 over square root 222, comma, -7 over the square root of 222. So these end up being our two unit vectors that are orthogonal to the original two vectors we started with. I hope you find this helpful.